Discrete compared to continuous. Discrete means the variables are 1, 2, 3, 4. They're never the numbers in between numbers. This example, how many TVs do you think will, what's the probability of us selling 3 TVs tomorrow or 4?
Whole numbers.
You know, whole numbers, right? Now, finite and infinite. Finite means that the only outcomes could be between 0 and 4. That we can't sell more, ever sell more than 4 because we only have 4 in inventory to sell. And so that's finite because tomorrow, how many TVs could we sell? Well, we could sell 0, 1, 2, 3, or 4, but there's no way we could sell any other different number. Okay. Now, infinite would be a situation where the number could be any number. It could go as high as possible. In this case, the number of customers arrive in a day. Maybe we usually get 20 customers a day or 30 customers a day, but there's nothing stopping us from getting 100 or 200 customers in one day, possibly. And that would be considered infinite compared to finite, where it could be any number. We don't know for sure. Nothing stopping us from having a maximum amount. Just want to make sure you get that definition. Here's a couple more definitions of comparing discrete variables to continuous. Notice the continuous, distance in miles from home to the store. Well, that could be 2.3 miles, 2.35 miles, 2.4 miles. Could be any number between numbers. But I like the top one, family size. Well, family size could be 1, 2, 3, 4, 5, 6. There's no way your family could be 2.35 or something like that. So that's discrete. All right, you ready? I'm going here. We decide to use historical information to come up with some probabilities of what could happen tomorrow. So we went back 200 days and counted how many TVs we sold every single sales day for 200 of them. And we counted them. 80 of them, crazy as it may be, we didn't sell any TVs. 50, 1 TV, and so on. We then converted those numbers to percent frequencies. 80 divided by 200, 50 divided by 200, 40 divided by 200. They add up to 100%. You ready? Based on historical sales, what's the probability that we're going to sell 4 TVs tomorrow?
10%.
10% chance, that's right. Let's keep going. Based on historical information, what's the probability that we're going to sell 3 TVs or more tomorrow?
15%.
That's right, you would add 3 TVs or more. Add that and that, 3 TVs or more. All right, let me ask it a different way. Based on this information, what's the probability that we're going to sell more than 3 TVs tomorrow?
10%. Because it's more than 3.
You got to hear the words, that's right. Before I said 3 or more, which was the 5 and the 10 add together, but this time I said more than 3. 3's out. It's only the 10%. This is the only one that could be more than 3. You're getting it. I want to make sure you're getting it. What's the probability that we're going to sell less than 3 TVs tomorrow?
85%.
Less than 3 TVs includes 2, 1, 0. So it's 40, 50, 60, 70, 85% chance that we're going to sell less than 3 TVs tomorrow. Everything that was included in that phrase, less than 3, is 2, 1, 0. You got to add those up. What's the probability that we'll sell between 2 and 3 TVs tomorrow?
45.
That's right, 2 and 3, 25. 20 plus the 5. Between 2 and 3 TVs tomorrow would be 2 or 3, really. You get it. Yep. You got the basis behind figuring out those probabilities when you're given the information like this. Now, what about uniform? The probability of us selling 0 TVs, 1, 2, 3, or 4 tomorrow are exactly the same. So how do we calculate the probability of selling 0 tomorrow? How many possible outcomes did I mention that could happen? That's right, 0, 1, 2, 3, 4 TVs are 5 outcomes. If you're told that it's the same probability for every outcome, called a uniform distribution, you gotta divide 1 divided by however many outcomes could happen. 1/5, 0.2, right? Is that right? Yep. 1/5, 0.2. There's 20% chance of selling 0 TVs tomorrow if every outcome has the same probability because they're uniform distributed. You know, it'd be like saying, what's the probability of me taking this die and rolling a 4? What's the calculation? That's right, 1 divided by 6, because there's 6 sides of the die. Every side has the same possible probability of happening. It's uniform. 1 divided by however many possible outcomes are in the story. There's uniform. These are easy. Now, expected value. You ready? Based on historical information, the number of TVs that we will sell tomorrow and their probabilities are here. They add up to 100%. We're either selling 0 or 1, 2, 3, or 4. To find the mean, you would multiply the outcome by its corresponding probability and then add those all together. 0 times 0.4, 1 times 0.25, 2 times 0.2, 3 times 0.05, 4 times 0.10, add together. The mean amount of TVs that have been sold over the last 200 days is 1.2. Now that's not discrete, but this is just a mean. It's not the actual data. The data is still discrete data. All right, we have that. This looks like that problem from the test. Now the variance. We take the mean we just calculated, 1.2, and we do everything just like everything you've learned in the previous chapter for variance and standard deviation, except for this one step. 0 minus 1.2, 1 minus 1.2, 2 minus 3 minus 4 minus 1.2, right? Because that was the mean. The extra step is, then you square it, well first we square it. The extra step is after we square it like we've done in the past, we multiply that square by the probability of that outcome, which add up to 100%. So this 1.44 times 0.4, the 0.04 times 0.25, and so on and so on. Now we add them. Where before we would add this column and we'd have the variance, but now we have these probabilities involved. We add up this column and we have the variance of this discrete data. There's the variance. Square root it, standard deviation. The only difference from what you learned before and now is this step right here where you're using these probabilities of each outcome involved. We got variance, we have standard deviation, we're already flying. Let's see, probability, uniform, we're at expected value, variance, standard deviation. Look at this. Look at this. Binomial distribution. All right, this is where it starts to get a little harder. You ready? This is a problem that you might read where it's asking you the probability, but the outcomes, there's only 2, and they're called a success and failure. I mean, hypothetical. Success and failure. Don't let the word success be literal. They're not always means success. It just means that success is the one outcome you're being asked about. For example, I can't think of an example off the top of my head, so I got to look at my notes because I wrote one down. It was, all right. What's the probability that this thing is not going to be defective? Now, the possible outcome is it's either can be defective or not going to be defective. See how there's only 2? But you're being asked about the not defective, so that's the success, I guess you would call it. But there's only 2 possible outcomes. It's not defective or it is defective. Here's another one. Okay? You're being asked about the probability of the golfer at this tournament. And we want to know the probability that this golfer that just is going up to the tee right now is using a Titleist. What's the other outcome that could take place? It's either they're using a Titleist or they're not using a Titleist. See how the question is being asked where there's only 2 possibilities? That's what makes it binomial. Now you recognize it as binomial. And then you have 3 different ways you can calculate the probability. Let's look at this example. Here's the formula, by the way. I want to talk about this, because one of the 3 ways you can calculate this on your test, and it's up to you, whichever one you find more convenient for you. There's going to be Excel, there's going to be a table in the back of your book, and there's the formula. And some people like the formula, even though this will take a little longer. Look at the variables. The N is how many there are altogether in the experiment. You're about to see where we're randomly select 3 employees to conduct this experiment. We're trying to find the probability of one of them no longer being with us, or the opposite would be they are still with us. They haven't left. It's about inventory turnover, or about employee turnover. Either they're with us or they're not with us. Success or whichever one we're being asked about. The X is whatever you're being asked the probability of. So the story's going to say, hey, we think we have 10% turnover here. We want to do an experiment. We're going to randomly select 3 employees. I just told you the N. 3 employees for the trial. We want to find the probability of one employee no longer being with us a year from now. You're being X is the 1. But in that story, I said, we think we have 10% turnover. That's the P. 0.10 is the P. 1 is the X. N is 3, because we selected 3, we're randomly going to select to watch for a year to see if they're still with us or not. And look at now, P to the power of X. P is 0.10, 10%, to the power of 1, because you're being asked about the probability of 1 no longer being with us. 1 minus P, that's 1 minus 10%, 90%, 0.9. Up there, that N minus X, 3 are in the experiment. We're being asked about 1. 3 minus 1 is 2. That exponent is N minus X. So we have, in the story, you have all the numbers to plug into that formula if you decide to use it. I'm going to show you the back of the book, and I'm going to show you Excel, which most of you, or probably all of you, will find much easier. Let's get to the story, though. You ready? This company, Evan, is concerned about low retention rate for our employees. In recent years, management's seen a turnover rate of 10%. The given probabilities, P's, just been given to you. They've seen a turnover of about 10% of their hourly employees annually, once a year. Yearly, about 10%, P. Thus, for any hourly employee chosen at random, management estimates that the probability is 0.1 that the person is no longer with the company a year from now. So they said, let's do an experiment. We're going to randomly select 3 employees at random. Took all the hourly employees, put all their names in a hat, randomly selected 3. Random process in any experiment has to be involved. And the population has to have an even chance of being selected in that random process. So every name of every hourly employee has to be in that hat. And every one of them has to have the same chance of being part of that 3, where the experiment has flaws. You everybody hear that? On randomness selection. We're going to randomly pick 3 hourly employees, and we're going to observe, and we want to know right now, based on the information we have, what's the probability that one of them will leave the company or be gone within the next 12 months. Now, the success is what we're trying to measure, which is the one employee being gone. I wouldn't say an employee leaving us in the 12 months is a success. That's why I say don't take it literal. The word success is whatever is being measured. In this case, an employee leaving is what's being measured. Either they're still going to be there or they're leaving. That's why it's binomial. There's only 2 possibilities here. They can't be, we're not going to count on leave of absence or something coming back. It's either they're gone or they're here. Still with us employed. Even if they're on leave of absence, they're still employed. So, if you use the formula, 3 factorial, 3 times 2 times 1 is 6, right? 1 factorial is 1. What's 0 factorial, just to remind you? 1. Okay, all right. Remember it. 3 minus 1 would be, because we used 3 employees in the experiment, we're measuring it, we're asking about 1. There's 2 factorial, 2 times 1. 10% is the given probability that we usually have in turnover. To the power of 1 is what we're trying to observe, we're being asked about. 1 minus the probability is 90%. To the power of how many are in the experiment minus how many you're being asked about. 3 minus 1 is 2. You do all the math on that, you get, usually you have 10% turnover. If you're going to have 3 random employees in the experiment, and you want to know the probability of 1 turnover, based on the given information, you usually have 10%, there's about a 24.3% chance that that employee will no longer be with us 12 months from now. Okay, you got it? Now, you go to page 651. Same story, but instead, I got to keep my page here. Oh, not in that book, I don't. All right, here we go. 651, same story. What was the given probability on the story that usually our turnover is? Yeah, I gotta get there. The table starts on page 651. Can I zoom this out? Right here. And I want you to notice at the top. See the P's across the top? This first page will only work if the given probability is somewhere between 1% and 9%. Our given probability is what percent?
10.
We got to go to the next page. Oh, wait, this one is still from 1 to 9. We got to go to the next page. Oh, this one's still 1 to 9. We'll go to the next page. And there we go. Now we have 10 through 50. And if you keep going, it will go up from 50 to something else, and so on. Now, look at the left side. You see a column that has N at the top and X. N is the number in the trial, which was how many employees are here? 3. You go down to 3. X is the number that we're trying to find the probability of which was how many? 1. Go to 10%, go down to 3, go to 1, 0.2430. The same answer we got when we did that long calculation.
How did we show our work for that?
Yeah.
You say I went to the table, N equals 3, X equals 1, P equals 0.10. Give me a page number or something, or just table something to tell me what you did. Show me each variable what it equals.
But if you do manually, it's going to be 3 points. If you go to the table, it's going to be 1 point.
But hang on, what you're confusing is no one gets penalized because the person who went to the table, their grades being divided by less points than the person who used things. So it's still the same. It doesn't hurt anybody because they went to the table and getting less points because they're divided by less points. I just want to make sure you realize there's no harm in you having 2 different grades. There's no harm.
So I think Excel might be slightly harder than this.
No, here's Excel. I got a blank sheet ready to go. You ready? Excel equals the Excel command. Thank you. The Excel command for binomial. You can't remember it. Just start typing the first couple letters. It'll give you a list and you'll recognize it. That's how I do it. B. I can see it already, but I'll do an I, and there it is. Binom DIS right there. And in fact, this one probably does the same thing right there, but I'm used to this one. You click on there, double click, and it opens up and tells you. It says, okay, number S, comma, trial, comma, probability of S, comma, cumulative. The first one where it says number, that is how many are you being asked about to find the probability. How many employees, no, not how many in the trial, how many are you being asked to find the probability about? 1. So the first number would be a 1. Comma. The second number is how many are in the experiment in the trial, which is how many employees? 3. The next number is the probability given at 0.1 or 0.1. I just put 0.1. Now, with binomial and Poisson, this last digit has a big meaning. If it says, what's the probability that 1 out of the 3 are no longer going to be there in 12 months, it's only asking about the probability of 1. So that would be a 0 on the end, which means exact for one number. But if the question said, what's the probability that 1 or more employees will no longer be there, 1 or less, let me go with 1 or less, then the last digit needs to be a 1. There's only 2 choices at the end there, a 0 or a 1. 0 means you're finding the probability of just one number. 1 means you're finding the probability of some number or less. 1 or less, 2 or less, 3 or less. Out of 3 employees, what's the probability that 1 or less? You need the probability for 1, and you need the probability for 0. And that's why you put a 1 on the end. So it will do both and add them together. Everybody hear that? So, I'm going to put a 1, 0 on that. Because it's asking for the probability that exactly 1 employee will no longer be there, right? We should get 0.243, just like the book, just like the thing. I want to notice, though, how different it is if I put a 1 on the end, because now it's going to mean what's the probability that 1 or 0 employees will no longer be with us out of the 3 after a year.
So it's lower percentage.
So it'll be higher percentage. Because the probability of just 1 no longer being with us is 24%.
I think it makes more with leaves.
No, now we gotta find the probability of 0 with it. So it's gotta be more. You ready? So I'm changing it to a 1. 97% chance that 1 or 0 will no longer be with us. And it makes sense because there's such a low probability of even 1 no longer being with us.
Can you even type true or false in that? Too?
Yes, you can. True
So
or
zeros,
false.
zeros.
But 0, 1's all that is.
Zero's true.
I don't want to confuse.
Okay.
That's right. That's right. I just don't want to. Now, here we go. I want to take this back. You ready? Right now, there's nothing there, right? No 0 or 1. The question says, you're going to randomly select 3 employees. Make sure we're okay. You're going to randomly select 3 employees. What's the probability that 1 or more out of the 3 will no longer be with us in 12 months? Now, everybody hear what I said? This is the first time you've heard 1 or more. Not 1 or less. 1 or more. You have this do the opposite of if it says or more. You have this calculate the opposite of the or more. So if I said 1 or more, the opposite would be how many?
2 and 3.
Less than 1, which would be 0. That's the opposite. So, I kind of know what you're saying. But I'm just going to go ahead and make this a 0.
1 or more.
Are you ready?
Oh, 0, 1.
Ready? And I'm making this a 1, even though a 0 would work. Whoop, whoop. Let me get on the other side of the comma. So now look at what I have typed in there right now. Yes, it's telling you to put true or false. I now have this set up to find the probability for 0 out of 3, which is the opposite of 1 or more out of 3, right? And then you just put right in front 1 minus. You're finding the probability of the opposite, and then you're subtracting it from 100% to find the probability of 1 or more. So, 27% of 1 or more leaving us. Let's do it again. You ready? Help me with this. You're going to have 3 employees selected at random. You're going to watch it for a year. Usually there's 10% turnover. What's the probability that 2 or more are no longer with us after a year? What's the opposite of 2 or more?
2 or less.
Not 2 or less. No. And if this were continuous, you could do that. This is discrete. 2 or more, the opposite is very distinctive. 1 or less is the opposite. I got to make this calculate 1 or less because it's the opposite of 2 or more. So to do that, this would be a 1, and this would be a 1. It was already. Now it's set up for 1 or less. 1 out of 3, usually 10%. Cumulative means 1 or less, so 1 and 0, which would be 90-something%. We already know that, right? Then you have the 1 minus in front. So now that you typed it for the opposite of the question, when you put the 1 minus in front, it's going to answer the question for 2 or more. The binomial distribution is calculating 1 or less, but we have 1 minus in front, which will give you the opposite, which is what we really want, 2 or more. So we get this. The probability that 2 or more are going to leave us out of the 3 in the next 12 months very small chance, 0.028, 2.8% chance, which is the opposite of 1 or less leaving us in the next 12 months, because we got the 1 minus in front. Got it. What if we're using the book? We're using the table. You ready? The question says, what's the probability? We got 3 employees. There's usually a 10% turnover. And I want to know the probability that 2 or more are leaving us in the next 12 months. Now, this is a little tricky with the book. You ever hear that? 2 or more. In the book, you got to look up the opposite and subtract from 100%. That's the only way you can do this. 2 or more. Or you're going to have to look up 2 or more. You have to look up 2, you have to look up 3, and add them together.
Yeah, 0.028.
Either way. But, you ready? So, these guys are saying, let's look up 2 or more. Go to the 10% column. We're going to 3 employees picked at random. Now there's the 2, 0.027. There's the 3, 0.001. You could add them together. Or, look at the 1 and look at the 0. Add them together, subtract from 100%. You'll get the same answer. Now where this comes in handy is, you gotta watch out, because sometimes you'll have, you ready? Let's go, well, you can't see all of it. Let's go 7. The question says, what's the probability you have 7 employees selected at random? Either they're gonna still be with us or they're not. Binomial. 10% turnover still. What's the probability that 2 or more will no longer be with us? Now, if this was a bigger number, you have to go and go, add this and this and this and this and this and this, or just add these 2 and subtract them 100%. Usually it's less work to do it that way. With Excel, you've got to do that 1 minus. And formula? In the formula, you would have to do the calculations for this, that many calculations, and add them together. Because that calculation is only for 1 number at a time.
If it's 2 or more, you just go with the probability of 2 and then 3 and then 4 and add
All those together.
and that's it.
That's it.
But if you want to
If you want to use the formula, you would have to calculate that one, then do it all over again for that. You'll get all these same numbers and then do them together. Or I would calculate that one and add them together, subtract them 100%. Much shorter route. That's right. The opposite of whatever the question is. Be careful on the words, because the question would say 2 or more, or it could say more than 2. 2's included in the one statement, 2 or more, but 2 is not part of more than 2. 2's not part of it. And with discrete data, that's a big deal. Continuous data, 2 or more than 2, are the same thing when we get to the next chapter in continuous. But with discrete data, they have very different meanings.
So you have 1 minus in front of the function because it's 100%?
Yeah, 1 is the
Okay.
100%.
Gotcha.
1 minus point something.
I was taking it as literally as 1, not 100%. Like
No.
I was thinking. Okay.
Yeah, 1 represents the 100%, because 1.0.
Yeah. I was just thinking 1 though, as a different
All right,
thing.
how do we feel? I think did we just finish binomials? No way.